The yo-yo. A yo-yo is made from two uniform discs, each with mass m and radius capital R, connected by a light axle of radius b. A light, thin string is wound several times around the axle and then held stationary while the yo-yo is released from rest, dropping as the string unwinds. Find the linear acceleration and angular acceleration of the yo-yo and the tension in the string. So we have two uniform discs connected by a light axle that is going through the centers, and we have a string wound around this axle, and you can see that as the string unwinds, the yo-yo will come down and it will be rotating basically in the counterclockwise sense, and the radius of the axle is b, and the radius of these discs are capital R. Okay, and this is our coordinate system x and y. Okay, so looking at it from the side here, side view, you can see that we have basically a cylindrical region, that's the axle, and we have the tension T on the string that is pointing up. All right, so if we write the net force on the y-axis, you can see that because we have assumed that the axle is light, so it's a light axle, we neglect its mass. However, these two discs have masses m each. It's a symmetric mass distribution. The center of mass will be right in the middle, and the total weight will be 2 mg, that is pointing down, and we have the tension in the string that is pointing up. So if I write the net force on the y-axis, sum of the forces y components will be 2 mg minus t in minus j hat direction, because the acceleration of the center of mass will be in minus j hat direction. So this will be equal to 2m times acceleration of the center of mass, where the acceleration is in minus j hat direction. And because this has no slip, acceleration of the center of mass is related to the radius of the axle. It's going to be equal to angular acceleration alpha times b. So we will see that we can also consider the torque acting on the system. The net torque will be provided by the tension, and from R cross T, if you point from the center towards the application point of the force, so for example, you can concentrate here and concentrating on the direction from the pivot point to the application point of the force, curling our fingers towards tension, the thumb points out of the board, but out of the page corresponds to this direction here, you can see, so that's in plus I hat direction. So it's going to be T times B times I hat. That's our net torque, which will be equal to the moment of inertia about the center of mass axis times alpha. And what is the moment of inertia? The moment of inertia is going to be equal to two contributions from each uniform disk. We have mr squared over 2 for the moment of inertia. So this is basically the result we found in problem 9.53. So each of this disk is rotating around its central axis. The axle goes through their centers. So the moment of inertia is with respect to this rotation axis, which is mr squared over 2. And we have two contributions, so it's twice this value. Then we can find that alpha is equal to TB divided by mr squared, because these twos will cancel, And notice that I have no contribution from the axle here because the axle was considered to be light, so we neglect its mass. Okay, now at the same time, acceleration of the center of mass is related to its angular acceleration alpha times b, so we can use this expression alpha times b, where alpha is equal to t b divided by mr squared. So now this is going to become m capital R squared tb squared over m capital R squared. Now we have the Newton's second law on the y-axis, 2mg minus t is equal to 2m times acceleration of the center of mass, which is 2m times tb squared divided by m capital R squared. So the m's will cancel, and we will see that if we collect all the tension terms on the right hand side, 2mg is equal to, in tension parentheses, 1 plus 2b squared divided by r squared. And this will give us, in tension parentheses, capital R squared plus 2b squared divided by capital R squared. Okay, so if we isolate tension here, the tension becomes 2mg multiplied by capital R squared. So it's going to be 2mg capital R squared divided by capital R squared plus 2b squared. This is our tension. And the acceleration of the center of mass then becomes, for tension we substitute this result, 2mg capital R squared divided by capital R squared plus 2b squared multiplied with b squared divided by m capital R squared. That's our result we have obtained here. So mr squareds will cancel, and we will be left with 2g b squared divided by r squared plus capital R squared plus 2b squared. Now, in order to get this dimensionally easy to follow, we divide the top and bottom with b squared. So it's going to be 2g divided by 2 plus capital R over b squared. Now you can see that this has the unit of acceleration, which is the unit of g. Okay. And the same thing we can do for tension here actually. So we can divide the top and bottom with r squared. So this would be 2mg divided by 1 plus 2b over capital R parentheses squared. This is a better way to report this result because it immediately shows us that tension has the unit of mg, which is force. The bottom is dimensions. Now the angular acceleration alpha is acceleration of the center of mass divided by b, the radius of the axle. So this will be equal to 2g divided by b divided by 2 plus r over b parentheses squared. So this would be our angular acceleration. Okay, now to summarize, we have a yo-yo that is made from two uniform disks. The moment of inertia of a uniform disk is mr squared over 2, that was found in problem 9.53. And we have two of them here that are connected by a light axle. So the rotations are about the center of mass. So we have two contributions. So it's going to be mr squared for the moment of inertia of the system. Because the axle is light, it has no contribution. A light thin string is wound several times around the axle, so the string has no mass either, and then held stationary while the yo-yo is released from rest, dropping as the string unwinds. So it's going to be rotating in the counterclockwise sense. Find the linear acceleration and angular acceleration of the yo-yo and the tension in the string. So first I have noted that the weight of the yo-yo is 2 mg, that is at the center of mass, which is right in the middle because we have a uniform mass distribution which is symmetric around the center of mass here. So it's 2 mg pointing down, and there's tension in the string that's pointing up. So 2 mg minus t will be 2m times acceleration of the center of mass. And at the same time, we have acceleration of the center of mass related to the angular acceleration alpha as alpha times b. So we will have the linear acceleration related to the angular acceleration. The net torque acting on this system is due to the tension. The tension is basically tangential to this circle when you view it from the side. So B times T in I hat direction is the direction of the torque, which is I center of mass times alpha. So we can obtain alpha here as TB over mr squared when we substitute for I mr squared. And acceleration of the center of mass is alpha b, so it's TB squared over mr squared. So this can be substituted into this equation. 2 mg minus t is 2m times acceleration of the center of mass, TB squared over mr squared. We can isolate tension from this equation, and we obtain 2 mg r squared over r squared plus 2b squared. Then I divided top and bottom with r squared in order to get this the dimensional consistency easily trackable, so I can see that this tension has the same dimension as the weight mg. Acceleration of the center of mass was alpha b, which is TB squared over mr squared. For t I substitute this result, and I then divide top and bottom with b squared, and I see that it has the unit of g, which is acceleration, 2g over 2 plus r over b parentheses squared. Alpha is acceleration of the center of mass over b, so it's 2g over b divided by 2 plus r over b parentheses squared.